powering the app economy. It's a big sentence, but what is actually the app economy? Well, we have millions upon millions of apps. I've used an app like 30 minutes ago to help me calm my nerves a bit for this presentation. I'm sure that most of you used an app to navigate or a transportation app to get here today. And we do this on a daily basis. We spend over 4 hours each day using apps. And each one of those apps is actually a business. We are at a reached stage where it's very easy to develop an app. There are millions upon millions being released every year, and it's just growing. But to make that app, that's a business, into a successful business, you need the right tools and the right partners. And this is where ironSource comes in. We empower app developers to turn their apps into successful businesses. Because out of millions upon millions of apps, you have to become that one app which will succeed. And this is where we come in. It's a platform, a comprehensive platform for both app developers and telecom operators, which contains a lot of solutions from marketing and publishing to monetization and analytics. And all of those can help you turn your app into that successful app. And because the app economy is so huge, for us data engineers, this presents an amazing opportunity because so many apps means huge traffic, and huge traffic means data challenges. And this is what we're going to share with you today. Those challenges, this huge traffic, is what forced us to become better at what we do and allowed us to have those amazing use cases to share with you today. So now I'm going to pass the baton to Rachel from Imply, who will share with you in a fun way what Druid is, a bit about Imply. And yes, floor is yours, Rachel.
Fantastic. Can everybody hear me all right? Loud and clear. Okay, can I get the thumbs up from the ironSource side? That you can hear me all right? Okay, fantastic. It looks like I can start. So wonderful. Well, welcome everybody. My name is Rachel Pedreschi, and I run the community team here at Imply. And what does that mean? That means that I get to work with some wonderful people in helping grow and expand the wonderful world of Druid throughout the world. And so I was tasked today to present in front of a group of people who, probably know Druid pretty well, but, give us a little bit of an overview, but make it fun. Everybody's had, a beer or an appetizer. So that's my challenge. And let me see if I'm able to rise to the occasion. So we're going to start with a little bit of a fairy tale, maybe a bedtime story, but in general, the Rise of Druid. So we're going to start with once upon a time, not so long ago, like the 90s. In a place not so far away, from me at least, Al Gore invented the internet. And it was good, at least initially. We could buy books and other people's used stuff and pet food and watch cat videos, thousands and thousands of cat videos. The internet was ruled by a ninja who sat in a Zen garden on the water. Their name was Oracle, and they charged the peoples lots and lots and lots of money to make this internet work. And the internet grew, as most good things do, and more people came to watch cat videos and use apps and buy and sell stuff and watch all fans and millions of cat videos. And very soon these inner tubes became filled with cats. But there wasn't enough money for the cat tube providers to pay the ninja anymore. until a benevolent dolphin came to the rescue. It was free and easy and made lovely little dolphin noises. Everyone loved the dolphin. The dolphin helped save the internet from the evil ninja and allowed little companies to do wonderful things. But a prophecy came upon the land by St. Jobs of Apple. It made the people slump and pray over these tiny devices that showed them hours and hours of cat videos. And now they could like those cat videos and comment on those cat videos, all while standing in lines. And the dolphin couldn't keep up with the tiny devices full of cat videos and people liking the cat videos and people sharing the cat videos. So they started doing horrible things to the dolphin. The Facebook in particular started taping it to other dolphins with scotch tape and thumbtacks. And the dolphins were sad and the people were sad because their books and other people's stuff, dog food and cat video likes were slow. A great new army arrived upon the land to save the dolphins and keep the evil ninja from taking too much money. Because at this point, the ninja had purchased the dolphin in a great coup they called acquisition. These new heroes called themselves NoSQL. A couch and a giant leaf emerged along with a cursed oracle called Cassandra and many others in this great battle to help defeat the oracle into making these applications distributed, scalable, and performant. They could even allow companies to pay for all the new hardware they needed with a wonderful invention called targeted ads. With the great success of the Facebook, new and wonderful ways to watch cat videos funded by these ads came TikToking along. Snappy chats and instant grams all made ad-sponsored cat video watching and sharing free and easy and maybe just a little addictive. Then, as their addiction grew, people wanted a way to ask questions about the cats so they could get better ads and find out the number of likes and even make sure their Netflix videos were perfect all over the world. But the NoSQL heroes didn't have those weapons. They were very fast at questions that they knew about, like managing one cat video at a time, but couldn't answer the ones with the math or the group buys or the huge table scans. The solution they had heard from the bards of the distant OLAP lands was a giant machine called ETL to move the data from their applications into ones like the dolphin into the form of a star. But the ETL machine was complex, and the dolphin and its friend Postgres soon buckled under the weight of all this internet and mobile data. They knew a new hero was needed. They looked around them, and the first thing they saw was an elephant. Yes, elephant's perfect. It's huge and never forgets, and it didn't need to seem to need that huge ETL machine. So they dumped all the cats into a lake in order for the elephant to manage the cats and to count the cats and group by the cats. And for a while, this was cheap and easy. So cheap and easy, they started putting everything in the lake. Everything. Cats, sharks, tacos, alligators, dust bunnies all ended up in the lake. But then this started slowing everything down. Seconds became minutes, minutes became hours. The lake became a swamp with too many things, but everyone's still wanting their answers done faster. To try to keep up with the constant amount of data and the need for a better ETL system, Kafka arrived to save the day, and all the things were now coming in faster, riding streams, and eventually overflowing the swamp lake. The elephant was too slow. The ETL machine was too complex. There had to be a better way. They searched the land for other ideas. They found time series, but knew from the NoSQL army that key value stores like these were based on couldn't answer the ad hoc questions. She also looked at what was left of Oracle, but even after all this time, it was still really expensive and couldn't scale. The Elasticsearch system seemed great. It could handle the Kafka streams and all the things in different formats, but the math and the ad hoc queries were hard. Then a wise figure descended from the cloud. The Druid had arrived to solve this problem. It could speak to the Kafka stream with exactly what semantics and also the language of the elephant's lake swamp, and allowed the people to ask all the questions of the likes and the group buys and the sums, even count distinct unrolled up data with a special spell called sketch and do it all in milliseconds, even at the scale of Yahoo and Netflix, and using actual SQL. Its magic lay in simple concepts done extraordinarily well. Cloud native microservices architecture, columnar storage, compressed and encoded data, roaring and concise compressed bitmap images, late materialization. The Druid knew how to wield this magic to control all the videos, count all the likes, predict the fraud, understand the ads. Soon the landscape changed from dark, murky swamps to beautiful flowing rivers of data. Data flowing through streams, the data river architecture, data flowing through streams and through lakes into an analytics database to power all the data-driven applications of your dreams. But you don't have to take my word for it. Druid is already used all over the world, all the time, to count all the things in an app that you just might use every day. Clickstream, ad tech, network monitoring, fraud analysis, application performance metrics, and all the data-driven applications that need fast real-time and batch native ingest from both Kafka and Hadoop, sub-second query response time, cloud native, and linear scalable architecture. So that is my story for today. You can find us in many different places on the internet if you haven't already. You can get involved on Druid Forum, on ASF Slack, on our new Druid Slack channel. There's some new accreditation programs available from the Imply website. Okay, well then, shall I hand it back to ironSource?
Here we go. Here in ironSource, we've discovered through user complaints that we've had very high query latency. And when I'm talking about query latency, it's not the same in Druid as it is in Presto or Spark or anything else. I'm talking about above 40 seconds in our use case. And above 40 seconds means timed out. We had, after thoroughly investigating, we saw that this wasn't an infrastructure issue, but a design issue. A flaw in the way we implement our data pipelines in Druid. We had to go beyond the traditional role of a data infra engineer and adopt a different mindset about looking at the data itself, looking at the users, looking at the usage in order to solve this issue. And this is what it helped us, enabled us to go from 35 seconds of average query time to 5 seconds of average query time. In the next few slides, next few minutes, I'm going to share with you how we did just that. We'll start with a bit of background, how we implement Druid here in ironSource. Then we'll talk about the issue that we've had, the high query latency, the user complaints. We'll go over what didn't work and then what did. But first, a bit about me. My name is Jonathan Kaplan. We met before. I'm a data infra engineer here in ironSource. And before that, I was a DBA team leader in the IDF and a data engineers team leader as part of a COVID-19 task force with the Ministry of Health. And another thing to know about me is that I hate when things go slow. It frustrates me. And when I'm talking about users, I'm talking about my friends, colleagues from my floor, started to complain about high query latency. It was annoying because Druid can be fun and it can be fast. And we went on a journey to make it just that. A bit of background. We use Druid in the same manner in all of our clusters. We ingest in a streaming method from Kafka into Druid, and we allow users to query this data using Pivot, which is an Imply provided UI, which allows users to run extensive queries without a single line of SQL. It's kind of great. Like, it doesn't matter if you have any background at all. You can just drop a field and it will generate a query for you. This cluster that I'm going to talk about is our largest internal cluster. I'm talking about largest and not busiest because it had a lot of data. And this is a lot of specs, but the only number you need to actually remember is 27. 27 data nodes that we've had on this cluster. Another thing we implement here in ironSource is Reindex steering. Reindex means that we aggregate the data again. So we do it, let's say, after a few days, we move the data from an hourly aggregation to a daily aggregation. This allows us better capacity planning and performance optimization when querying this data. which leads me to the issue that we've had. Users were complaining about high query latency, and we already covered how much of an annoyance that is, because Druid is fast as hell when it's done right. So we started investigating. And being infra people, we started to investigate infra-related symptoms. And we found an issue. We saw that we have a Reindex lag. I just covered that Reindex is the thing we run in order to improve query performance, right? We had a 60 days lag out of 90 days of retention. This is massive. It directly affects our performance. So we opted to solve this issue, this infrastructure issue. We scaled out the cluster and we allocated a lot more resources to each Reindex task in order to allow them to close the lag, which it did after a few days, but performance improved only by a tiny bit. So where does the issue lie? Why is everything running so slow? Well, as I said in the beginning, the app economy is massive. It has huge traffic, and traffic grows every day. More traffic leads to more rows in the database. It means that when querying those rows, we have more scans, which directly leads to more I/O, and this means higher query time, right? The problem is that we already outscaled the cluster and did all the infrastructure tunings that Elad, which is the talk after me, will cover. So we had nowhere to go in the infrastructure level. There was no infra issue. This is where we had to do a mind shift. We had to adopt a different way to look at these performance issues in Druid. And instead of focusing only on the infrastructure side, we had to focus on the data pipeline itself. It's a thing we call know your data. And because the data flow is what it is, it's a flow which started at the beginning, which is the ingestion from Kafka. Our original topic in this cluster, or in most of those other sources, was a central topic. What is a central topic? It means a busy topic. It's a topic that contains a lot of messages that we don't actually need to consume. And it's a topic that contains a lot of columns that we don't actually need. It means that Druid had to spend a lot of resources and time to filter those messages out. By creating a new dedicated topic, which was pre-filtered, meaning only the messages that we actually need, we were able to increase the ingestion rate by two times faster. It's doubling the ingestion rate, which is incredible, but it's not related to performance, right? The reason I'm telling you this is because this laid the foundation for the next changes we're going to do. We had to move a lot of things and make ingestion a heavier process. And this change laid the foundation that allowed us to do just that. Which leads me to the first optimization thing we did related to performance. Kafka by default produces in round robin. And because Druid ingests per partition, it aggregates per partition that it ingests from. By moving to a partition key, we were able to reduce our aggregation in ingestion from 0.8 to 0.4, which is the same thing we have post-compaction, meaning that we aggregated the data in the ingestion level as best it can be. But it wasn't enough. We had to go a bit deeper. When I'm talking about deeper, I'm talking about what is actually being ingested into Druid, which is cardinality. We saw, after analyzing the data and analyzing how the dimensions actually work, we saw that we have specific dimensions that dramatically affect the aggregation. They break it because they have a lot of values. We can't remove those columns because they are being used, right? We have analysts, product managers, developers, our users, they need those columns. What we can do is reduce how it affects our aggregation. We combined different values and removed unnecessary values, and this allowed us to go from 0.4 to 0.3 in our aggregation ratio. This includes both ingestion level and post-compaction level. This is great, but we're not there yet. We're still very far from where we want to be. But where can we go to now? Segments are optimized. Everything in the infra side is great. There's no load average issues. Data is aggregated properly, and we improve that. And there is no more index lag. So where does the issue lie? Users know best. And you have to know the usage and know the users. Well, when you have a lot of noise, and noise, I'm talking about a lot of complaints. When you have dozens of users complaining about performance, it's very hard to understand what they're actually complaining about. So by identifying key users and mimicking the way they query Druid, we're able to see which dimensions are slower than others. And we did. We saw that we have dimensions that are much slower compared to others, thanks to those key users. But what do they have in common? All of them use expressions in the query level, which is basically query level expressions. But what are expressions? Expressions are any manipulation you will do on the raw data itself. It's joins, calculations, concats, cases, and anything you can think of that is not actually being saved into disk. Sorry? Okay. The problem is that doing them on the query level consumes a lot of resources. It takes time. So we decided to do a test and to see what is the effect of this change. We decided to move the joins into the ingestion. When talking about joins, I'm talking about lookups. But what are lookups? Lookups are key table values, key value tables in memory. Let's say we have the idea of an application, and we want to show the user the name of the application. So when they query the field itself, in the background is being joined through the ID to the name. Thing is, this is a very resource and time-consuming operation. So by moving them into ingestion, we achieved something incredible. We improved query performance by 50%, which is massive. It's a huge drop. And this is the first major change we actually saw in our query performance optimizations. So naturally, let's move all of them, right? And by moving all of them, moving all the other expressions that we've had, we were able to reduce the latency, basically improve the query performance by 50% again. We did not expect this. This was a big surprise to us. We thought that the lookups were the issue, and we said, okay, let's test everything there. And this is massive. And this is how we went from 35 seconds of average query time to 5 seconds of average query time. To summarize, this is a simple checklist that you can implement in your Druid clusters. And we are implementing them now as we speak to our Druid clusters, to all the rest. We understood that scaling out is not always the solution, and it will not solve any issue that we have. Sometimes it will solve. A bit of a teaser to what Elad will talk about. But in this case, it wasn't the solution. We learned that our monitoring is lacking because we had a huge reindex lag, and we had no idea. This thing provided a huge opportunity for us to redesign the way we monitor Druid, and we now did a complete revamp in the way we monitor Druid. By reading from clean, dedicated Kafka topics with partition keys, we optimized ingestion to the max, meaning that the rate itself is so fast that any change we did, moving everything to ingestion, didn't impact the rate. It's massive. We had to go beyond infra-side level because partition keys and dedicated topics is a bit of infra still, but we had to understand what is actually being ingested. We had to understand the data itself. And by understanding the data, we were able to reduce the cardinality even more. And last but not least, and the most important here, is cleaning your queries. By moving everything to the ingestion level, by saving everything in disk instead of running it in memory, this is what allowed us to make this thing go so fast. Because as I said in the beginning, Druid can be fun and it can be fast if you do it right. Any questions? אני אתרגם. The question was, out of all of the changes that we implemented, which was the biggest change, and which had the biggest impact? And the answer to that is moving everything to ingestion. Cleaning out the queries, making them run as vanilla as possible, just reading from disk, saved us a huge overhead in resource consuming on the infra side. Like in the end, it was an applicative change which did massive infrastructure improvements. Okay. The question was that when we move everything to ingestion, how did it actually affect the ingestion rate, right? To make it simple. So as in the first slide as I showed in relating to Kafka, we talked about the clean topic. And this clean topic, by moving to that topic, the huge improvement that it did on the ingestion rate itself is what actually allowed us to do all of those heavy changes. Because you are right, moving lookups and calculations to ingestion is a heavy process. But when we optimize ingestion, we didn't see a major effect. And because lookups themselves are being loaded into the ingestion tasks themselves, it's a bit different from the way when you do it in a query time. So it's a different way to implement it.
Were there any transformations that you wouldn't move back to ingestions?
The question was that if we had any transformations that we could have moved into ingestion. And basically, there are two answers to this. The first one is no, because we moved all of the ones we identified as problematic. And yes, because it all depends on the usage. Like we could move things into ingestion because we decided that saving everything in disk is good enough for us. If you have currently constantly changing data in lookups, which changes the data in the disk itself, maybe it's not the right way for you to implement it. Maybe you need to solve this in a different way. But because we neglected to decide that we had to move everything to ingestion. And having, even if it was a one error margin on specific lookups, we accepted that error margin.
Did you have to change any settings of the ingestion peon? That's the first question. If so, were the performance of the peons affected in any way?
The question was, did we have to do any changes in the parameters of the peon itself, in the ingestion spec? And in the ingestion spec, and how would it affect the performance, right? Okay, so there was a couple of changes we had to do in the ingestion side itself, which the first one is it's actually not related to ingestion, it was related more to lookups. We had to increase the timeout when the lookups are being loaded. Because when the ingestion tags, the peons are starting to run, they load the lookups. Before that, we had a zero timeout. We didn't allow any timeout to happen when using lookups. But when we moved them to ingestion, we had to give them a bit of leeway, a bit of time to load them. So we did this change. The other change we did is a thing that Elad will cover a bit later, which is reducing the handoffs. Increasing the handoffs, making more handoffs. No more questions? Any other question from the audience? Yes. תוריד מסכה, אני לא שומע פשוט. שאלתי בעברית חופשי, אני אתרגם. Okay. The question was, how would we handle the thing that I just said? Because we made it that the lookups take a bit more time to load, how do we handle this in a real-time environment? The quick answer to this is it's at the most a 7 seconds wait for the lookups to be loaded. It depends on the cluster, right? In some clusters it will take 7 seconds, in others it can take 2 seconds. It depends on how many lookups and how big they are. Yeah, it's everything in second. We use Druid in our use cases. We use Druid strictly for real time.
How does this change your working process in terms of getting the requirements for the topics? Did it change? Would you do the same?
The question was how these things change the way we interact with other groups relating to Druid. And the answer to that is that we have, compared to before, we were just focused on the IFRA, and it was like a black box thing. We could just throw whatever into the Druid, and we couldn't care less. We had to do this mind shift. So now we are actually part of the design process with product and with the developers themselves. And when we have a new data source or a new cluster, a new business, we are part from this design from the beginning to the end, from where the Kafka will actually be, how the topic will be, how many partitions, how much data per second. Like everything is, we are part of the conversation now, and this improves both sides. It allows the developers to go much quicker into production because we are together in this, and it allows us to better plan the clusters. The question is in the case when the lookup changes, let's say an ID remains the same, but the name changes. How do we handle this kind of scenario? And there are two ways to solve this. The other one is to make a business decision that the data was at the time is static. And the other one is to fix it using Reindex. You can reindex all the time, and you can actually use Reindex with lookups to do the changes again. Any last questions? Okay. Thank you. And now we're going to do a fun giveaway. Might not be that much fun, but it's something. It's a Druid question, so you have to know what I'm actually talking about to solve this. The question is, how many rows did we actually save? When we have 5.98 trillion rows before aggregation, how many rows were actually being saved to disk when the ratio is between 0.01 and 0.2? It's impossible to know the answer. It's like a guess. So now you can just, scan this and insert your answer. Yeah. Okay. I'm going to repeat the question again, and I'll show it again. The question was, how many rows did we actually save? When the aggregation ratio is 0.01 and 0.2, between 0.01 to 0.2. And it's a guessing game. Like there's no actual way to know the answer to this, except if you're me. So the only way. Did everyone scan? Okay, so thank you again. And we're going to have a 10 minutes break. There is Malabi here, for those who like it. And yeah, bon appetit.
Okay, so now for the second use case from Iron, which is finding performance bottlenecks in our Druid cluster. My name is Elad Eldor. I'm the data infrastructure team leader in ironSource. So the story I'm going to tell you now is about a cluster, a different cluster than the one that Jonathan talked about, in which we started with an average query time of very high, which was 50 seconds. And this doesn't include the queries that just crashed on timeout. After tunings we managed to make all the queries end, and they ended at about 20 seconds. So let's see how we diagnosed the issue and also how we solved it. This talk will be separated into four topics. The first one is the performance aspects. Which performance aspects we looked for when we diagnosed the issue in the cluster. The second one will be the tuning we made in order to improve the queries in the cluster. After that, we'll describe the effect of these tunings on the performance aspects, and then we'll sum it up with what we learned. So let's start with the performance aspects. We have 4 aspects. The first one is the traffic and CPU usage into the cluster. The second one is the aggregation ratio of the cluster. Then we'll talk about the query usage and latency. And afterwards, we'll describe the segments that were scanned and the scan time. Let's start with the first one. So how I'm going to show you the performance of this cluster will be using a graph with 2 y-axes. And I'm also going to compare the performance of this cluster, the network cluster, to 2 other clusters we have, which is IAB and SDK. These are 2 clusters with much more traffic coming in, and the network has much less traffic. So the blue line, you can see the blue line is the traffic in the data source size, and the red line is the number of cores. So we are showing not only the comparison between this cluster and the other 2 clusters, but also a comparison between the data coming in and the number of cores into the cluster. So in the case of both the big clusters that have good query latency, queries running faster, we can see about the same ratio of data source size to number of cores. While in the problematic cluster, we see that the ratio is opposite. We have much more cores compared to the data source size. However, the performance here of the query is really bad. After the tunings we made, we had to increase CPU even more, from 400 to about 700. This was because the historical processes, which process most of the data in the cluster, just used all the CPU, which is CPU user time, not system time or interrupts or waiting time. So we just had to increase the number of CPU. The I/O is not an issue. Again, the CPU usage is not going on wait time or system time or interrupt time. It is net user time. No, the reason is totally CPU user time, not CPU wait time. We use SSDs, and in this scenario, in Druid scenario, the I/O wait time, the disk utilization, what you see in IOStat, for example, is very low. Unlike a similar system, Kafka, in which the wait time is really critical, not in this case. So, although we added, in my team, we are very, very sensitive to costs. We don't like to add cost to the cluster. We like to reduce. But in this case, we had to increase the number of CPU cores. However, we didn't want to pay linearly as we added more cores. So what we did, as you can see, we added 73% more cores, but paid only 56% more. How did we do it? This is interesting. We switched the instance type. Instead of using i3-8X, we used i3 metal. So we scaled up the instances, but we scaled in the number of machines. Why we did it? Because other companies using a bigger Druid cluster than ours have noticed that they can pay less with the same number of cores if they scale up the machines. The reason for that is probably the fact that with less machines, we have less shuffles within the machines. This is theoretically, but we also see this phenomena that with the same number of cores, but bigger machines, we have the same query latency and pay less. No, yes, 10 gigahertz, but we have more cores in the i3 metal compared to the i3 8 large. No, it's okay. You can. It's okay. Okay. So because you have less machines, there is less. Yeah. Okay, so I'll there is, like in Spark, when you have more machines, there are more. It's harder for all the machines to update. So in total, you get more shuffles, not just operations of shuffle, but also the data being shuffled is greater. It doesn't remain the same. So eventually, this is probably the main cause why with 20% less cost, you reach the same query latency. This same theory applies also to Spark. We've seen this in Spark and we see this also in Druid, and also Imply sees it. And also customers with hundreds of machines, both on-prem and cloud, also saw this. So it's like a rule of thumb that you better start with less machines, but bigger ones instead of many small machines. Also, it's good for your cluster to have as few machines as possible, especially if you are on-prem. And many run Druid not only on AWS, but also on-prem. So this was the first aspect. So the ingested data is not the reason why this cluster is slow, because this cluster hosts much less data, receives much less data than before. So let's look at the second aspect. Maybe it will shed some light over why the cluster is slow. Let's look at the aggregation ratio. What is aggregation from the get-go? So Druid receives data. This is the ingested data, but then it tries to aggregate it in order to have less data. What it does, it takes several similar rows or identical and compacts it to one row. And the aggregation ratio really tells how much Druid succeeds in aggregating the data. So in both clusters that we compare ourselves to, aggregation ratio is not so bad, 60%, 50%. In our problematic cluster, aggregation ratio is really bad, 23%, which means that almost all the data coming in is the data being queried. After the tunings we made, we didn't succeed to increase the aggregation ratio by much. In most cases, this is a problem. Aggregation ratio, which is low, is a problem. In our case, it's not a problem because the ingested traffic is already very low. So again, also the aggregation ratio, the low aggregation ratio is not the cause for the slowness. So we looked at another aspect. Maybe this is the reason for the slowness, and it is. This is the reason. Here we can see the number of, both the number of queries per day, the number of subqueries per day. This is the blue line, and the red line is the average query time in both peons and historical. Just as a reminder, the peons are the processes that query the real-time data up to the last 1 hour, while the historical serve all the rest of the data. So, and also we have the number of subqueries in millions. So you ask yourself, do we run millions of queries each day? Of course not. But each query in Druid is split into many subqueries. So here we can see that although these are the cluster that receives much more data, the number of queries on them is really low compared to this cluster. It's like 7x more queries. And also the subquery time is much higher. This was before the tuning. After the tuning, the number of subqueries remained the same. However, the subquery time reduced by half. So a multiplication of number of queries and the subquery time leads us to understand why this cluster is so slow. In the case of the P98 query time, both in peons and historical, I mean, the two highest percentage of queries, the situation was even worse. We had subqueries reaching 8 seconds. And after the tunings, it was also reduced to about 3.5 seconds. So this is the reason why the query is slow, but it took us time to understand this because we thought, okay, we have a cluster that receives much less data than the other clusters. Why is it so slow? It took us time to figure out that we don't need to look at the ingested data, but we need to look at the load of the queries. The fourth aspect is the most interesting one. Segments. What are segments? Segments are the smoosh files. If you know Kafka, then it's like the log files in Kafka. So segments are the data that Druid queries when it receives query. Like now, how does it work? Peons receive data from Kafka. Then they, after some period of time, they offload the data into the deep storage, S3. Then the historicals, which are the real workhorses of Druid, they take the data back and put it as segments in the disks of the data nodes. And then when we have a subquery, the subquery scans the segments. So in the big clusters, the number of segments is the black line. We can see the black lines are lower compared to the network. In the network, although we have much less segments, it scans more segments, which is obvious because it hosts much more queries. And also the segment scan time is higher. However, after the tunings, look what happens. The number of segments being scanned has tripled. It tripled because the tunings exposed the bottleneck that we were not aware of. This issue, for me at least, it is the most interesting one, and we found it only when we prepared the meetup. I mean, after we did all the tunings, queries were faster, but we didn't fully understand until we read the data again in order to prepare this meetup, and we found out that the number of segments just tripled. The reason is that the bottleneck that we discovered, that we solved, exposed why many queries just failed on timeout because they didn't have time to scan all the segments they needed. They scanned only this number of segments and not this number. So the tunings allowed the class to scan all its segments. Excuse me? Next section. And also, again, I would like to emphasize the mistake that we did, the pitfall that we did in order for you not to fall into this pitfall. We looked at the traffic instead of the query load. So here we have the black line is the number of segments being scanned, and the light blue line is the number of ingested segments per hour. You can see that in both SDK and IB cluster, they have more traffic than the network cluster, but less queries. In the network, both before and after the tunings, the ratio is opposite. We have much more queries running on the cluster and much less data ingested into the cluster. So if you go with one thing from these performance aspects, is don't look only on the ingested data, look also for the query load. Now, which tunings did we make in order to improve the situation? We did 3 major changes, both in hardware and ingestion. On the hardware side, as I explained before, we added more CPU. So we added 73% more CPU, more cores, but paid only 56% more because we switched the instance types. We scaled up, both scaled up and scaled in the cluster. On the ingestion side, we did 2 things, and I explained each of them. First, we reduced the hand of segments. Now, what is the hand of segments period? Hand of segment period is that when the peons read the data from Kafka, they after some time, after configured amount of time, they offload the data into the deep storage. And then the historicals read this data and put it as segments. So what we discovered, which is not mentioned in any Druid formal documentation, is that ingestion tasks don't deal with queries well as the historical. Historicals deal with queries much better than the peons. So what we did was forcing the peons to read less, to offload the data much faster to the deep storage. And in order to enable the historicals to read, to serve queries on more data. So instead of, let's say, half an hour end of segments period, we reduced it to about 10 minutes. In the ingestion parallelism, we increased it. Why? In order to let the real-time query, the peons, to handle queries faster. Although even after the increase in parallelism, again, they don't know how to serve queries well as the historicals. Now let's look at the effect of these tunings on the performance aspects. We'll start with what remained the same. The number of subqueries before and after the tunings remained the same. We have 7x more queries on this cluster compared to the other two clusters. The number of ingested rows, like the traffic coming in, and the aggregated rows also remain the same, and it is very low compared to the other clusters. What was increased? So the number of CPU cores, we added more cores, and the number of segments being scanned was also increased from about 100% more to 800% more, which is the most interesting stuff, at least from my point of view. What was reduced after these tunings? The query latency was reduced by 2.5x. The average subquery time and the P98 was reduced by 2x, and the segment scan time was also reduced by 2x. So let's summarize what happened here. After the tunings, we remained with the same traffic and the same load. The number of segments scanned was tripled. The segment scan time was reduced. The subquery time was reduced, both of them by half. And two impacts. First, we don't get queries to terminate on timeout. And second is that the total query time reduced from 50 seconds to 20 seconds. So notice that we added only about 50%, let's say 60% more cost to the cluster, but we reduced the time by 2.5x. This is another example that throwing money on a cluster is not a solution for everything. And usually what we do when we try to tune data, tune the cluster and not pay money. But this is a rare case in which we had to add more cores. But we added it not linearly to the improvement we made. But we don't settle on 20 seconds. We want Druid to be really real time. So we are doing we intend to do three major changes, then like Jonathan talked about before. First of all, we are moving lookups from the pivot to the ingestion tasks. Then we will produce to the topic by partition key in order to reduce the aggregation ratio, and by this reduce the time it takes for the ingestion to handle the data. And at the end, we try to find popular dimensions and reduce the cardinality in order to reduce the amount of data coming in. Any questions? So I guess no one understood anything. Okay, so thank you very much. And now let's move to our special guest for tonight from Lyft. I really appreciate what they did on their work on Druid. It took some time to get them, but eventually they agreed. So please welcome Tian Yu from Lyft talking about their Druid cluster.
Hi everyone. Thanks for having me here. And I'm Tianyu from Lyft. And today I'm gonna talk about building data pipeline using Druid at Lyft. And a little about me. So I'm from the data infrastructure team at Lyft, and I'm currently working on Druid and Trino. And for today's agenda, I'll briefly talk about why we choose to use Druid at Lyft. And we will go over the Druid architecture, especially how we set up the real-time and the batch ingestion pipeline, and also the Druid setup in Lyft. And last, we will go over some use cases, like where we use Druid. So first is about like why we choose to use Druid. So Lyft mission is to improve the people's life with the best transportation. And to achieve that, we will need the support of the data. And there's lots of like business needs. For example, the real-time geospatial data for the market analyze, and also we need the fast internal tour for the data exploration and the visualization. And we find that Druid quite fit for those use cases and the business needs. And we also compared the query performance with Trino, and we find that it's more than 10 times faster. And it's mainly because like Druid has those like in-memory data caching without shuffling among the serving nodes. And also it provides the direct memory maps on the broker side to boost the performance. And we also compared the price, and the Druid actually costs much less than DynamoDB. And Druid has very reliable service, and also it has the support for tiering, so that we can provide like more tighter SLs for specific use cases. And like we can always add more historical nodes or middle managed nodes to horizontally scale at runtime. And the Druid has those like native support for the JSON HTTP and the SQL via the JDBC. And also the native support for the batch ingestion and the real-time ingestion also help us building those like pipelines. So this diagram is basically a very brief overview of like how we build the real-time and batch ingestion pipeline. Basically, we use the Flink and Kafka for the real-time and Airflow and Hadoop for the batch ingestion. So this one is actually a more detailed diagram of our real-time ingestion pipeline. So basically, in Lyft, we have a bunch of like application which generates like plenty of the analytics event, and we send them to the AWS Kinesis, and we have like a service called Fanner to do a bunch of event processing, and then like send it back to the Kinesis. So for our Flink application, we basically use those like AWS Kinesis as the source to like get those data. And like what Flink application will do is it has the functionality to like allow us to enrich event and also do the data transformation based on the Flink SQL function. And also it can allow us to apply some UDFs, the user-defined functions as well. And we also do some sampling and filtering for the data. And eventually the Flink application will transform the JSON format data to the protobuf type and send it to the Kafka sink. And on Druid side, we use the Kafka connector to have those like real-time events actually land on Druid. So on the Kafka side, we use the one-to-one maps, which basically like one topic, like well maps to one data source in Druid. And on the Druid side, we use the custom role passer to deserialize based on those like protobuf messages. And it also like support for the schema evolution. And apart from our Flink application, we also allow our user to spin up their Flink application and build their own business logic upon that. And so allow them to send those data to the Kafka, which will eventually be picked up by the Druid. And apart from that, we also had a like Druid controller, which allow us to submit supervisor to the Druid overlord. And this will like allow us to kick off those like real-time ingestion job. So next I'm gonna like talk a little bit of some like steps of like how we onboard a real-time ingestion event. So first, we will have to define the protobuf definition for our Druid data sources. And the second step is an optional step. It only needed if there's any like transformation or data enrichment needed at the Flink application. And in this example, for example, we will have to transform into a geohash. So we use the Flink application to like pick up those SQL query and run at the execution time. And we will also have to specify a configuration file. In that configuration file, we will have to identify which protobuf message it will be mapped to, and also which column will be the timestamp column and which columns will be the dimensions or matrix. Here we don't have those matrix, so I didn't put. You won't see them in the example. And also we will have to provide the query granularity and the segment granularity. And the very last step is to trigger the event ingestion to Druid. Basically, it is done via submitting the supervisor to the Druid overlord. And we basically do so at the deployment stage. It will automatically deploy it and submit to the Druid overlord. But we can always like run those commands manually to submit a supervisor. Next, I'm gonna talk about our batch ingestion pipeline. Here in Lyft, we used the Airflow to do the scheduled work. And basically for Druid batch ingestion, we create some specific Airflow DAGs, which will submit the job to the overlord, Druid overlord, and then have those like map reduce job run in Hadoop. So this is actually used for three major cases. First is for the batch ingestion. Like we basically handle like some offline massive data in that way, because we don't like those data actually don't have the need to get the most recent data, and we basically run the batch ingestion every day to have them like ingested in Druid. It actually saves a lot of traffic, and we don't need to go through like the real-time ingestion pipeline to do so. And the second is to do backfill. If there's any real-time pipeline incident happened, we can always use that to avoid any data loss. And the third is we also use the batch ingestion pipeline to do the compaction. We like find out that in this way it can like significantly reduce the total segment number and total segment size. And there's a bunch of benefits we can get by applying the batch ingestion pipeline. First is we find that the query performance got improved after like we do the compaction. And also for those like data like ingested via the batch ingestion, they have like fewer segment number and better aggregated, and their total segment size is also smaller. And the system's reliability also got improved because we find the historical nodes reboot time got improved since there's like fewer segments to load. And like with fewer total numbers of the segment and also the fewer total size of the segment, the storage also reduced, and it saves us a lot of money. So here is about some Lyft Druid setup. So basically, we use the open source project to generate a Debian package and deploy to a set of Lyft Kubernetes pods. So we used to use the EC2, but we successfully migrate all the Druid cluster to Kubernetes on the beginning of 2021. And here are some like Kubernetes settings. Basically, we used the same CPU and memory, similar CPU and memory members as the previous EC2 type, instance type, but we also made a little bit of the tuning. There are two more things to call out here. One is we use like a hot tier historical nodes and also like the hot tier broker nodes to support specific use cases because our they want to have some like resource isolation and have like a tighter SLs, and in that way we can like better support them in this way. And second is that we use the router to specifically connect to Mode, which is a data visualization application. And we do so via the Mode bridge, and also we use the Avatica JDBC driver. And we use the MySQL RDS to store the Druid metadata information. And we use the Zookeeper to do the leader election for overlord and coordinator. And we use the S3 to do the like deep storage and Flink and Kafka for the real-time ingestion. And next, I'm gonna go over some like use cases where we use Druid at Lyft. First is we use Druid for some interactive dashboard. So for this specific example, it's about a geospatial data looks up. So in Lyft, we had a requirement from some operator because they want to find a driver in a given geospatial. We used to use DynamoDB as the database to support that, but we find out that it's kind of hard to model those like time series data in key value databases. And also the DynamoDB's cost is like a lot. And we eventually migrate to Druid to store the location information of the last 3 months. And we have like hundreds of thousands of records to be ingested per second. And we managed to have the P50 query latency less than 100 millisecond and P99 to be less than 200 millisecond. And because those like data are ingested through our real-time ingestion pipeline, the data freshness is less than 1 minute. And as we can see from this like screenshot, it's pretty easy to use. The operator just needs to draw a diagram, and the application will automatically like filter all the driver within those like geohash for them. And the second use case is we use Druid to do data exploration, analytics, and tracking. So this is a screenshot from Mode, and we use that to do like infra span tracking in Lyft. And we basically build those like Mode dashboard on top of Druid data. And as I mentioned above, we actually use the router plus like Mode to connect with the Mode bridge to connect with Mode. And then we have those like Avatica JDBC driver to do so. And we use the batch ingestion job to load the data from Hive to Druid every night. And we managed to have the P99 query latency to be less than 1 second. And we can always like quickly retrieve the infra-span information and show it to our user. And the third use case is we also use Druid to do some market forecasting model. And there's a specific use cases where some user came to us and they want to like make some prediction for the Druid business matrix, for example, the rideshare demanding or pricing, etc. And they have very like tight SLOs, and they want to ingest like over 100K rows per second and have like more than 400 requests per minute. And they also wanted to have the ingestion data freshness to be less than 10 seconds and have those like query latency P99 to be less than 500 milliseconds. And in order to fully support with those like tight SLs, we create like dedicated hot tier broker and historical nodes for them. And also let the user to spin up their Flink application to kind of reduce the data freshness for that. We also compared the Druid with DynamoDB on these use cases. And the query latency is kind of similar, but the Druid is like more than 40 times cheaper than DynamoDB.
Thank you very much, Tianyu. I wanted to open you a chat now, but I think people are listening to us for more than 2 hours. But we have many questions for you in a private talk. So again, thank you very much. We really appreciate that you joined us today. So now for the winners, it's for the winner. Should I guess who is the winner? Maybe. טכנולוגיה חדשה, sorry. Okay, so first place is Barak Ben Natan. Second is Tomer Levy, and third is Maor Lampert. So that's it, and thank you very much for coming. The answer is 358.8 billion. Yeah, there was 0.06 aggregation ratio, which is very, very high, by the way. So it's very good. Oh, what's the prize that you? Oh, no, this is the first prize. Oh, this is the first prize. This is headsets of Sony, our sponsor for today. And they didn't pay us anything. And North Face, Druid, this is, we have 3 winners, but 2 gifts. So 2 people will need to split it. Oh, okay. So this is the first prize, Sony and bag, and places 2 and 3 will get also a bag. That's it. So thank you very much for joining. Good night.